Hi folks, and welcome back to Physics with Captain Rod. I'm making this video here to provide a couple more examples of how to study the motion of an object. So this particular problem has a little background history to it. Many years ago when I was in high school, my buddy Trapper, he was driving his parents' Honda Accord, and he came around a corner and there were a couple cows in front of him. He hit two of them. Nobody was hurt, minus the cows. When I asked him, Trapper, how did you manage to hit a cow? He said to me, and I quote, "They darted out in front of me." And anyway, the Honda Accord was destroyed. Trapper wasn't hurt. The cows were destroyed as well. Anyway, that story has lived on in history as I have created example problems out of this ever since. So let's see here. Let's go over this. My buddy Trapper says he was going 55 miles per hour when he came around the corner and saw a cow in the road. Actually, there were two of them, but I only put one in my example here. Trapper's going to apply the brakes, and that's going to accelerate the car, in this case in the opposite direction of the velocity, which would be to the left. And what we're going to try to calculate is the acceleration needed to keep that cow safe, assuming that the cow is 100 meters in front of Trapper when he applies the brakes. So, all right, first thing we're going to do here is get our units consistent here. Since we have the distance in mile per hour, the first thing we're going to want to do maybe is convert that speed to meter per second. I'll do this right here. So we got 55 mile over hour. And again, the conversion factor to get rid of the miles, we'd be multiplying by 1,609 meters in 1 mile. And then to get rid of the hours, we would multiply by a conversion factor with 1 hour up top and 3,600 seconds. 3,600 seconds in the bottom. And when I work this out, I get 24.6 meter per second. So there's Trap's speed when he comes around the corner. Now again, when you're studying the motion of an object here, remember you're studying the relationship between position, velocity, acceleration, and typically, against how they're varying with time here. So as far as position here, what I'm going to do is put a coordinate system origin where the car starts, call this the positive x direction. All right, so we're using x to keep track of the position of the car. Motion diagram is also an important thing here. So at this instant here, the car's moving pretty fast. So I'm going to use this dot to represent x. Now remember, when you're drawing motion diagrams, think about a digital camera taking photos. Click, 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 click at equal time intervals and superimposing the pictures. So here's my first location for the car. The first time frame goes by, maybe the car is here. Next time frame, now the car is slowing hopefully. So the delta x's should be getting smaller. Again, so these distances, these are changes in position, or what I'm calling delta x's. Now, what we're going to try to find here is the magnitude-wise, the minimum acceleration to keep that cow safe. So what we're going to do is we're going to use the 100 meters for the displacement. And let's go ahead and now draw our velocity graph, right? So again, graph of velocity against time. At t equals 0, our car is moving 24.6 meters per second. So let's put this up here somewhere. 24.6, and I'll just put the units off to the side, meter per second. Now, presumably the car is stopped, hopefully short of the cow. So we're going to kind of look at the limiting case like it stops just short of that cow. The time we do not directly know. So that'll be kind of an unknown here, which is fine. But the velocity when it stops is 0. So again, coordinates on our graph here. This would be the point 0 seconds, 24.6 meters per second. And this one right here, this is the point t, which we don't know, and 0 meters per second. And we'll go ahead and use our standard constant acceleration assumption, which means that's a linear graph. Okay, so remember now, how do we calculate displacement? So our displacement, which is our delta x, which is the 100 meters, as far as this graph is concerned, that's equal to the area under this curve here, which is going to allow us to write a nice easy equation for this. It's a triangular area, so 1/2, and then I would call this distance here the base. I'll go ahead and put that in red right here. So that distance is our base, and I'll even put it red in the calculations, which is t, which is an unknown, which is just fine, times, oops, let me do this here. I'm going to color code this. The height, which is this distance. I'm going to go ahead and even put this in green in my equation here. That's the 24.6 meter per second. And there we go. So we have an equation there for t. Go back to my color I like for just writing. So if we solve this for t, and I'm going to go ahead and leave the units out for just a minute. I'm just going to put NCU, which stands for note consistent units. We'd be multiplying by 2 and dividing by 24.6. So that's going to give us 200 over 24.6. Ooh, boy, I can write that better for sure. Give me a moment here. Over 24.6. Now, unit-wise, that'd be 200 meters, divide by, and that 24.6 has units of meters over seconds, and you'll notice this comes out to seconds. And what I get out of this, if we do this right, is 8.13 seconds. Now, that's not directly what we were asked. We're asked for the acceleration, but you know, physics problems are a lot like puzzles, and you know how once you find a piece to a puzzle, they get a little bit easier. If you can calculate any quantity typically in some sort of physics problem you're working on, the difficulty typically gets cut in half. Right? Now that we have the time, the acceleration is easy to calculate. Because remember, acceleration is delta v over delta t, and as far as this graph is concerned, that is the slope. And I'll go ahead and go back to my color coding, even the numbers here. All right, so our delta v, it's this distance here on the graph, and keep in mind we're going from plus 24 down to 0 meter per second. So that delta v is minus 24.6 meter per second. Go ahead and divide by the delta t is this distance, and I'll even make the color match the graph. This distance here we now know to be 8.13 seconds. And we work this out. Let's see, we get minus 3.02 meter per second. And I like to write my units like this. And again, if you want to write it meter over second squared, that's perfectly fine. All right, what does the minus sign mean? It means opposite. All right, it does not directly mean left. It means opposite of what we're calling positive. We're calling right positive, as we can see right here. So in this problem, it does mean to the left. So the acceleration needed to keep that cow safe, I'm just going to write that as approximately 3 meter over second squared to the left. So an acceleration of 4 will give us even more wiggle room there for that cow. All right, well, let's take a look at the next example here on my handout. Okay, so this one's going to require a little bit more screen size here. I'll start it like this for now. Okay, at the instant shown, the car on the left is at rest. That's referring to this one right here, not moving. This guy right here, not moving. That's the car on the left. The one on the right, that's this one, is traveling at 20 meter per second. At t equals 0, the driver of, again, this car here hits the gas and accelerates at 5 meter per second. Where will the cars meet, assuming they start 100 meters apart and the velocity of the car on the right remains constant? So give me a moment here to kind of set this up. All right, so what we're going to do, just like previous examples, first we're going to define a coordinate system. So let's go ahead and put this right here. We'll call that the positive x direction. Now let's write down conditions for these cars. So at t equals 0, this car, its x coordinate is 0, and its velocity is 0. All right, this car starting from rest. All right, this car, however, at t equals 0, the car on the right, oops, don't do that. At t equals 0, that car has a velocity of 20 meters per second, and it's to the left. So in this coordinate system, if we're attaching a number to it, that'd be minus 20 meters per second. So the minus sign is how the direction is taken into account. And the original, or the initial x coordinate is plus 100 meters. Because this distance in our problem, 100 meters. Okay. Now, it's going to be a little tricky to try to get all of this on the screen. But what I've done here is I've drawn 4 graphs here. So what I'm going to do is I'm going to make these graphs match these cars. So we're going to draw a velocity graph and a position graph for the car on the left. Then we're going to draw a velocity graph and a position graph for the car on the right. I'm going to sketch these now. All right, so this car right here starts out with a velocity of 0. But this car is accelerating. Now, the trick to this is we don't know the time when they're going to cross. So what we're going to do is we're going to make this kind of generically. We're going to put a point out here, and we're just going to call this t, unknown. And then the y-coordinate is v. I'm just going to call that v, again, unknown. So these are the points t, v. And these are unknowns in this, and that's perfectly fine. Constant acceleration assumption. Now, the acceleration we do know. The acceleration of that car is 5 meters per second. So what that's going to do is that's going to give us the equation of this line. Now, there's a couple ways to get that. I'm going to take the quick short route here. This is a linear function. So its mathematical form will look like this. V equals something times t plus something. And remember, the acceleration is the slope of a velocity. That's this number here. And the intercept, I'm going to read it right off the graph, is 0 meters per second. Whoops. And I'm just going to put NCU for note consistent units here. So the equation of this line is V equals 5t. Now, you can get it this way. You can also use area under the acceleration curve to get that. And again, I got more videos on how to do that. Let's go up here and talk about the position function here. So at t equals 0, that car starts out at 0. Now, this car is accelerating, so this car's position graph is going to look something like this. It's going to have curvature because the motion diagram for the car, the green car, is looking like this. And again, those delta x's are going to get larger as time goes on for the green car, meaning that, you know, if I pick 2 points as we go from here to here, that's the delta x, right? And that's the delta t, and those delta x's are going to get larger. Then we can get this function from area under this curve here. So again, our delta x is going to equal, now this is a triangular area, so 1/2, the base is this thing we don't know, t, and then the height is this distance, that's a velocity that we don't know, but it's described by this function, so 5t. And if we simplify this, keeping in mind that x initial is 0, this delta x will just become x, because delta x can be written x final minus x initial, which would be x final, which is this, minus 0, equals, and by the time we multiply this out, we get 2.5t squared. So there is our position function for the green car. All right, red car. Velocity of the red car, remember it's 20 meters per second. It's right here, it's 20 meters per second, and it's to the left. We're taking that into account with a minus sign relative to our coordinate system. So put this down here, and it's constant at minus 20, and again, units are meter per second. Out to some time, we'll just call it t. Now, as far as finding equations here, right? So our delta x, again, this is for the red car, is going to be given by this right here, which is minus 20 times t. And that delta x is x final minus x initial. Now for the car on the right, the x initial is 100 meters. Oops, sorry about that. So if we solve this for x, we get minus 20t plus 100. That's a linear function with a negative slope. So come up here and we'll start graphing it. Right, at t equals 0, that car was at 100 meters. And again, this has negative slope, so maybe something like this. And again, we're just trying to make this stuff match. Now, there's no reason to put it down to the 0 because physically, again, they're not going to cross here. They're going to cross, somewhere in the middle, not the middle like 50 meters, but somewhere along here at an unknown x they're going to cross. So there's no reason to put that crossing the axis. All right, so now what we're going to do, and I'm kind of running out of room here, we're going to equate the x coordinates because when these cars meet, and they're going to cross one another, they're in different lanes, by the way, we're not going to get ahead on, but their x coordinate is going to be the same. And I'll go ahead and put this right here, I guess. So that's going to give us the function on the left, 2.5t squared. We need to be equivalent to the function on the right, or the same. So minus 20t plus 100. Now, these cars, when they cross here, right, our x coordinates are the same, and this equation needs to be solved. Now, this is a quadratic, so what we want to do is make it look like a quadratic. So let's write this 2.5t squared plus 20t minus 100 equals 0. And what I'm going to do here for the sake of simplifying this down is just get the results of this written out here. If you solve this quadratic, you're going to get two roots, one positive, one negative. We're going to take the positive root because our time is starting at 0. And I think I got 3.48 out of that. Having trouble reading my own writing, but something like that. And then once we get this time, we can go to either our position functions to get the x coordinate. And since this is sitting right here, if we take this time and run it through here, x value that I get out of this is about 30 meters. I'm going to put a little qualifier here. Again, I'm having a little trouble reading my writing, but if you take this time and you don't get exactly 30, I probably just misread that a little bit. It's definitely 3 point something, but I believe it's 3.48 meters. So again, the point of this video was just to provide more examples of how to use velocity graphs to study the position of an object. And as you look at all these examples, notice some things that are common to both of these problems. Let me go back to the simpler one, right? You always define a set of coordinates. See how that's been done here and here. Let me undo those two things there. Okay. You want to always put the initial conditions in for both particles. You'll notice that here, I guess I didn't explicitly write it here in the first one, but at t equals 0, the x coordinate of this car is 0, and the velocity is the 24.6 meter per second. Over here at t equals 0, all right, the information is written for the car on the left and the right. Then you want to sketch those velocity graphs and then use concepts of slope and area to write your equations, right? And an important thing here is that when time is unknown, this will become a variable here, right? Just because you don't have a number doesn't mean you stop. You just label it t and move on. Then typically you're using the area under the curve to write a equation about the position of the particle. And if you need another equation, you would use the slope to write an equation for velocity, time, and the acceleration. So again, just example videos of how to do what I call these motion studies here. I guess I'm pushing 20 minutes here, so I think I'm going to end that right now. I hope that these videos are helping you learn how to do this stuff. Have a great day.